All right, so welcome everyone. Thank you so much for letting us take over your math club for today. So for those of you who don't know, we're running a graduate student class on what is whatever your favorite notion is. And Sean has prepared a talk for us today on what is constructive mathematics.
Hello. All right, so first off, I just want to thank you all for being here, whether you're from Math Club or from the What Is seminars. I really appreciate seeing everyone. Okay, so today I'm going to be talking about what is constructive mathematics. And to start with, I'm going to give you a bit of history as to the subject. So constructive mathematics began in the early 20th century with people like Brouwer, and then it started to grow in popularity in the mid 60s with people like Bishop. But then, in a surprising turn of events, most of the constructive mathematics moved from being done in math departments to CS departments. And it's only recently that it's been growing in popularity again among mathematicians. And as a result of this switcheroo, there's a lot of misconceptions mathematicians have of constructive mathematics that have sort of been brewing for a few decades. So my goal of this talk is to, well, first of all, I really like constructive mathematics. I think it's really neat, but also I want to sort of tear down some of these misconceptions that people have and try to show ways in which constructive mathematics is actually useful and not just like a weird way to challenge yourself in mathematics. Okay, so first off, let me give you a bit of background for this. This is a field that deals with logic. So here's some introduction to logic stuff. These are some of the rules of logic. They are not all of them. This is not exhaustive in any way. These are just some of the big things. So the first is modus ponens, which corresponds to the rule that if P is true and P implies Q is true, then Q is true. This is a standard rule, a standard action that you've probably seen in logic. There's also law of non-contradiction, which corresponds to saying that it is not the case that P is true and not P is true. And then finally, we have the law of excluded middle, which corresponds to the case of saying that P or not P. So these are some of the standard logical assumptions we take when doing mathematics. And they're so standard to the point that most of the time you never actually consciously think about them. They're just kind of things that you use without even regard to the fact that they are actually axioms. So in classical mathematics, and so here I'm referring to classical as the mathematics you're all familiar with, which I will later contrast with constructive mathematics. You have modus ponens, you have law of non-contradiction, and you have law of exclusion. But in constructive mathematics, you have modus ponens, you have law of non-contradictions, but you do not have the law of excluded middle. You do not assume the law of excluded middle in constructive mathematics. You have all the other logical axioms you take. It's just specifically this one. So in constructive mathematics, it is not valid to assert every proposition is either true or false. That is just one of the axioms that we're restricting ourselves from using. Okay, so now we can start talking about some of the misconceptions that people have about constructive mathematics. Misconception one. We assume the law of excluded middle is false. This is not the case in constructive mathematics. We are not assuming that the law of excluded middle is false. We are just not assuming it is true, right? So it's in the same way that if you're talking about a group, for example, you can assume it's abelian, but you could also just not make any statement whatsoever about whether it's abelian or not abelian. And one of the benefits about this is that something that you prove about a group without assuming it's abelian or not abelian holds true in the case when it is abelian and when it's not abelian. So one way, one of the abstract benefits of constructive mathematics is that any result you have is applicable to cases both when the law of excluded middle is true and when it's false, as long as all these other axioms are also assumed. All right, but then misconception number two is that we can never use law of excluded middle in constructive mathematics ever. Now, I need to qualify what I mean by using law of excluded middle. What I'm saying here is that we can say that a proposition is either true or false if we can prove that's the case. There are situations, for example, if you're talking about two natural numbers, the proposition, the two natural numbers are equal or they are not equal, can be proven. We can actually show that that specific application of log squared middle is provable without actually the log squared middle. So in classical mathematics, we simply invoke log squared middle for that. In constructive mathematics, you have to put in a bit more elbow grease, but it does pop out. So we can use log squared middle specifically when we prove it. It's not that you can never even talk about that P or not P statement. You just have to show that it actually exists. All right, so number 3, this one's slightly different, but it's the misconception that constructive mathematics is philosophy. Now, this is understandable because back in the 20th century, especially with people like Brouwer, constructive mathematics had very close ties to philosophy, specifically what's known as the intuitionistic school of philosophy. Nowadays, however, this is not the case anymore. Modern constructive mathematics has completely diverged from its philosophical roots. There are people who do constructive mathematics now with no regard or claim to the fact, to thinking that classical mathematics is unfounded or not valid just because it uses the log squared middle. This is just another area of math that people like to do in modern times. Right. So finally, this is related to the second misconception. It's the misconception that we cannot do proof by contradiction. And this one's a bit different from the others because it is true in a certain sense of proof by contradiction, which is not the one that you're familiar with. Almost really. All right, so let's get into this. Also, if anyone has any questions, feel free to blurt them out. You don't need to. Yes.
Can you comment on this relationship with homotopy type theory?
I can comment a lot, but can we say that till the end just because that's a bit derailing from the way I'm going for. But yes, there is a lot in common it has with homotopy type theory. All right. Okay, so proof by contradiction is usually formulated as this style of proof. We assume a proposition P, we derive a falsehood, which I'm just representing as false here. And then from this, we can conclude not P. So this is normally how we use proof by contradiction in classical mathematics. We assume P, we show that it leads to a contradiction, and thus we conclude that P is false. But in constructive mathematics, proof by contradiction splits into 2 different cases. So the first case is now known as proof of negation. And the reason it's called this is because this style of proof is exactly how you prove a proposition is false. You show that assuming that it's true leads to a contradiction, and thus you can conclude that it's false. The second case has a few different names. The community is not actually fully decided on which name you call it. Proof of, I like the name double negation, but you'll also see proof by contradiction as just referring to this specific one. So this is what I mean when people say you can't do proof by contradiction in constructive mathematics. When they're saying that, they mean you can't do this style of proof by contradiction. And so this one is of the form you assume not P, derive false, and then conclude P. All right. So you may be looking at me like, wait a minute, I pulled some kind of sleight of hand. These are saying the same thing. You're saying that, okay, you assume P is false, you derive falsehood, and you can include P. That's the same as saying, instead of assuming P, you assume not P here. You derive false, and you conclude not P. And surely not P is the same thing as P, right? No. In constructive mathematics, this is actually equivalent to the law of excluded middle. So this is known as double negation elimination. Right, run out of space. elimination. And it's specifically the rule that not P implies P. It turns out double negation elimination, the rule is saying that if P is not false, then it's true, is equivalent to the law of excluded middle. So if we assume double negation elimination, we are doing classical mathematics, whether we want to or not. And as a result, proof by contradiction does split into two different cases. So now when we assume not P and derive false, all we have proven is the double negation of P. We've proven that not P is true. But then we cannot conclude P from this because that requires double negation elimination. And so as a quick example of what these are, you can prove a number is irrational by assuming it's rational and deriving a contradiction. That's exactly how we prove a number is irrational. But you cannot prove a number is rational in constructive mathematics by assuming it's irrational and deriving a contradiction. This is where it gets a bit tricky, because this is completely unintuitive from a classical mindset. All right, so sorry, 1 second, my timer. Okay, so now I'm going to give one final example of how constructive mathematics can define intuition. And this is because the fact that we can't use law of excluded middle, while being non-intuitive, it also destroys a lot of mathematics that we do. And that is because we use law of excluded middle in places that we don't really think we do. So here's this example, the intermediate value theorem. We all know it. We all love it. And in constructive mathematics, we do not have it. The proof that we normally use for the intermediate value theorem does not work in constructive mathematics. And to see this, I'll give this a quick sketch of the proof, right? So we have a function from the real numbers that's continuous. Okay? And then we say we have 2 points, A and B, such that f of A is negative and f of B is positive, right? And the usual statement of the intermediate value theorem is that there exists some point in between A and B such that f of that point is 0. There's a root of f in between these 2 points. And classically, if it's constructive, it has to connect here without having any jumps. But the standard style of proof is saying, okay, consider A plus B over 2, right? And now we case on what the value of A plus B over 2 is when f is applied to it. So what is f of A plus B over 2? So in the case when it is greater than 0, right? We can repeat what we just did on the interval A plus B over 2. Because now, since A plus B over 2 is positive, we can repeat this process on this part. If it's negative, on the other hand, we repeat on A plus B over 2, comma B. And so this is because from the same idea, we have that it's negative, then this also satisfies our initial condition, and we can repeat the process. And then finally, we have that if it equals 0, then we're done, right? Like we can end early. So see if you can spot where this falls apart in constructive mathematics. It's right here. It is not true that any real number is either equal to 0 or not equal to 0. That's using the law of excluded middle. We do not have that f of A plus B over 2 is either equal to 0 or not equal to 0. So we can't actually proceed in this case. We just can't move forward. This proof doesn't work. It doesn't mean that the intermediate value theorem is false. Because again, classical mathematics is constructive mathematics with the law of excluded middle. So we can't prove it's false in constructive mathematics because it is true in classical mathematics. This proof just doesn't work. All right, so that's an example of where constructive mathematics sort of breaks some of the existing. And at this point, you might be thinking to yourself, why are we doing all of this, right? Like, I just put out a bunch of math canon. Constructive mathematics, since we don't have the law of excluded middle, it's like we're doing mathematics with like one hand tied behind our back, right? Like, what's the point of restricting ourselves in this way? Well, it turns out that in some situations, you have to use constructive mathematics. You no longer get a choice. Classical mathematics does not work, inconsistent. And so in these situations, you are forced to reason constructively. So I'm going to go delve into an example of this, which is known as synthetic differential geometry. All right. This is a good time to ask any questions because I have a lot of erasing. So. All right. Synthetic differential geometry. All right. Let's try to unpack what this means. So synthetic refers to the process of when we take a mathematical field, we abstract it away to some fundamental set of axioms that still captures the structure we want. So synthetic is an abstraction of an existing mathematical field that sort of preserves the key structure that we want to talk about.
Where by field time you mean area of map?
Area
or
map,
field
yes,
number?
yes, like homotopy theory, or differential geometry, stuff like that. Not an actual field. So a good example of this is Euclidean geometry. Euclidean geometry, that is not a mess. Euclidean geometry is in fact synthetic. And the reason for this is because points and lines in Euclidean geometry are just abstract notions. Points and lines don't specifically refer to points and lines. So points and lines don't specifically refer to points and lines on a coordinate plane. They just refer to mathematical entities that satisfy the axioms of Euclidean geometry. One way to see this is the coordinate plane didn't exist in the time of Euclid. There was no Cartesian coordinate plane. Descartes was a long time away. So that's an example of a synthetic mathematical field. It's geometry, but you're specifically working with just abstract things. So synthetic differential geometry is the same idea. Synthetic differential geometry is the same. To see this, well, basically, instead of points and lines being the abstract notions, we have smooth maps and smooth manifolds. So smooth maps and smooth manifolds are the abstract notions in synthetic differential geometry. This is because smooth maps and smooth manifolds are what classical differential geometry says. So it makes sense that this is the exact structure we would want to abstract. Okay, so right. Let me give you some intuition behind some of the key ideas in synthetic differential geometry. So in introductory calculus, we generally think of a function f from real numbers, that is differentiable at a point x. As being a function such that if you look at the graph of f, and we look at the point x, and the tangent line of the graph of f at this point, if we zoom in, we get that the graph of f at this point is approximately the tangent line, right? And this is exactly how we formalize limits. We say that it's approximately in line, and then we can start doing stuff that's more complicated using sort of this rigorous notion. So the idea with synthetic differential geometry is to add more points to the real numbers. You add smaller infinitesimal points such that you can zoom in even closer now on the graph of f, where the tangent line is now exactly the graph of f in this infinitesimally small neighborhood. And by doing this, now we no longer have to talk about limits. We can just zoom in close enough to get it exactly. We can define the derivative by just saying it's the slope of this tangent line, because that's what the graph is at this point. So that's some of the intuition. Now we can get into how this is actually defined. So I said that we're going to add more points to the real numbers, and because of this, we're going to call it a different name now, because it's the same intuition as real numbers, but it's a different object. So this is known as the smooth real line. And I'll write it slightly differently. Smooth real line R. So first fact about it is that it is a constructor field. So what do I mean by that? Well, remember how I was saying that in constructor mathematics, a lot of classical intuition breaks down? Turns out we have to be a lot more careful by when we say field. So a constructor field has all the same ring structure that you expect. The issue is the divisibility. The way we formalize divisibility in a constructor field is we say for all x in the smooth real line,
Now field is field.
this is the field. Yes. If x is not equal to 0, then x has an inverse. And I'm just writing this as shorthand for x has a multiplicative inverse. It has all the properties you'd expect of a multiplicative inverse. But so now we're saying that in constructor mathematics, the notion of a field is such that the divisibility rule says that if x is not equal to 0, then we have an inverse. And that's just how we formalize it. In normal classical fields, we don't actually even think about this. It's just one of the definitions. If it's not 0, then it's like it's multiplicative inverse exists. But we have to, I'll get to why we're formalizing it like this. Yes.
Yeah, I'm sorry. I don't see why this is different from the normal formulation, right? Because you always in a field 0 is never good.
Yes, you're right.
So
The issue is I wanted to make it very clear when x is not equal to 0, we get this, right? This is because, as we'll see later, this is a particularly subtle notion as for x not being equal to 0. And there are some things that you might think are initially invertible, but they're actually not. So I'll get into that real quick. Let me know if you still have any questions after that. So we have the next key fact about the smooth real line is that there's an infinitesimal space now that's defined as every epsilon in the smooth real line such that epsilon squared is equal to 0. This is our infinitesimally small neighborhood that we use to look at like to zoom in even closer to f. And so this is actually making rigorous the notion that a lot of physicists have, where you consider a small deviation that squares to 0, right? And so this is not a coincidence. Synthetic differential geometry was designed or was found basically because Lauber was looking at a way to formalize physics in like a specific way. So this is not a coincidence that this is the intuition a lot of physicists use. This is just a way to make rigorous that intuition. All right. Because of this, we can now get to. Actually, I want to leave this picture here, so I'm going to try to squeeze it in here. So now we're going to get to the crucial axiom of synthetic differential geometry. And this is an axiom because constructor mathematics includes classical mathematics. This just doing constructor mathematics. I guess because I was saying we're going to have an example where we have to use constructor mathematics. This is because we're going to get an axiom that conflicts with the classical mathematics. So this axiom will basically be the thing that forces us to use constructor mathematics. And I'll actually get into why in a minute. So this is known as the Cook-Lauber axiom. And so what this says is that for all f, and then from the smooth, for all functions from the smooth real line to the smooth real line, there exists a unique point on the smooth real line such that for all epsilon in delta, f of epsilon is equal to f of 0 plus this point, this m times epsilon. And we generally think of m as being the slope. So this idea right here is just making rigorous this notion that we have over here. Because we say that when we zoom in close enough, this is just a straight line. What this is saying is that if we just evaluate f on these infinitesimal space, it's exactly the straight line that intersects f at 0 and then has some constant slope of m. And so we actually define the derivative of m at 0 as being m. This is how we define the notion of derivative. All right, so one thing you'll notice from this is that we didn't say anything about f. We didn't make the assumption that it's differentiable or continuous or anything like that. And that's because this axiom implies every function is differentiable. Every function from the smooth real line to the smooth real line is differentiable. And not just that, it's smooth, it's infinitely differentiable because this derivative is a function from the smooth real line to the smooth real line. So it's differentiable and so on and so forth. This is the anti-classical part that I'm getting. Because in classical mathematics, any function from the, because in classical mathematics, not every function from the real numbers to the real numbers is differentiable. We get a contradiction if we just try to import all of classical mathematics. But that's still not like exactly clear where this breaks apart. So that's actually what I'm going to spend much of the remaining talk on. Okay, so let's yes, okay. So now I'm going to go into an example, a list of examples that are sort of build to a big point that I make. Any questions so far? So, example 1. Delta, the infinitesimal space, is not just a set with 0. And so the intuition behind this is because if it was just 0, it doesn't really make sense to zoom in on the neighborhood of delta. It would just be a single point. So to show this, again, so okay, just for clarification, not equals is the same as not delta equals 0. So this is actually the same statement as not delta equals 0. That I just want to make sure that that clears up because it is important to sort of keep track of this. So, I can leave that there. So, proof. Again, because it's a negation, we can use proof of negation for this. So we assume delta is equal to just 0. Okay, so now consider the function from the smooth real line and smooth real line. That's just the identity function. Thank you. Okay, so we can consider the identity function on the smooth real line, right? And so we have by the Kuhn-Glauber axiom that for all epsilon in delta, f of epsilon is equal to f of 0 plus f prime of 0, because again of how we defined the derivative, times epsilon. F of 0 is just 0. So this is just equal to f prime of 0 epsilon. But we could have also just plugged epsilon directly into the identity function. So because f of epsilon is just equal to epsilon, we get that f prime of 0 of epsilon, the times epsilon, is equal to 1 times epsilon. And so because over here we state that m is unique, that's the unique slope, we get that f prime of 0 is equal to 1. And that this strategy is actually how we usually derive the derivative. We show that the derivative is equal to two different things, and thus we can conclude this, right? But now we get to the contradiction. So since we're assuming delta is equal to just 0, for all epsilon in delta, f of epsilon is just equal to f of 0. right? Because any point in epsilon is just going to be 0. So we get f of 0, f of epsilon is equal to f of 0. But this is just equal to 0. Again, suggestively written as times epsilon. So, because again, 0 times epsilon is equal to f prime of 0 times epsilon, because the Kuiper-Lauber axiom guarantees uniqueness. Yes,
Sorry, isn't epsilon an element of this triangle? So epsilon must be 0. So how are you allowed to conclude that f prime of 0 times epsilon equals 1 times epsilon implies f prime of 0 plus 1?
Yeah.
You're not allowed to divide by that.
yeah. So what we're doing is we're saying f of epsilon. So f is the identity function, right?
Okay.
So this top part is all actually correct. You can do this top part without assuming this. What this is saying is that f of epsilon is equal to, on one hand, f of 0 times epsilon, f prime of 0 times epsilon. On the other hand, it's just equal to epsilon because f is the identity function.
Mhm.
So we have that it's both equal to f prime of 0 times epsilon
But then,
and 1 times epsilon,
how are you allowed to go to that application?
because this is unique. Because we have that for all epsilon, f of epsilon is equal to 1 times epsilon. So the uniqueness statement that says that there's a unique point in R. So this is what this means.
Yeah.
Unique point in R such that f of epsilon, such that for all epsilon in delta, f of epsilon is equal to f of 0 plus m times epsilon. Because this is unique, if there's any other m that satisfies this statement, it's equal. Yeah. So this is actually can be thought of as a universal property.
Right.
Yeah. So then when we start invoking the property of the delta, we get that f of epsilon is just equal to f of 0. And then we can conclude because f of 0 is 0, we can write this as 0 times epsilon. And then by the same argument, we get f prime of 0 is equal to 0. All right. And then from this is actually not bad because u is equal to 1, which is a contradiction by the axioms of the field. X. So you get a contradiction, and thus we're done. We've shown that assuming delta is equal to the set with just 0 leads to a contradiction, and thus delta is not equal to the set with only 0, which is good. This matches our intuition. We don't want delta to just be 0 because otherwise this axiom makes no sense, right? So now you're thinking, all right, we showed that it's not just a set with only 0. So can you give me an infinitesimal that's not equal to 0? No, you can't. Let's go into one. Okay, so I'll try to leave this bottom part because it is useful. So now we have our second example. Example 2. For all epsilon and delta, we have that it is not true that epsilon is not equal to 0. And so this is a negation. So the proof goes by proof of negation. Proof, assume epsilon is not equal to 0. Okay, then by the axioms of the field, because smooth real line is a field, right? Epsilon minus 1 exists. This is why I was being a bit nuanced about the definition of a field. Because epsilon is not equal to 0, the multiplicative inverse of epsilon exists. So because of this, we have that 1 is equal to epsilon squared times the inverse of epsilon squared, right? But this is also equal to 0 times epsilon inverse squared. Because again, since epsilon is in delta, and delta is defined as being the infinitesimal space, the space of all points whose square is 0, we get this equality. And then we get that this is just equal to 0, because any number multiplied by 0 is 0. So we get that 1 equals 0 again, which is a contradiction. And thus, we are done. All right. Now something funky is happening here, because we showed that epsilon is not 0, right? But we also showed that delta is not just a set with only 0. And the reason this is consistent is because we can't conclude from this that epsilon is equal to 0. We can only conclude it's not 0. And this is where the check mathematics portion Here's the thing. Because, this is the really fun part. We have this wonderful theorem. In synthetic differential geometry, the law of excluded middle is false. And we can prove this just using what we have here. So here's the proof. Again, it's a negation. So to prove this, we assume that it's true and derive a contradiction. So assume law of excluded middle. And then now we're going to construct a little lemma, right? So for all epsilon and delta, we can apply law of excluded middle to get epsilon equals 0 or epsilon not equal to 0. Right, this is just a proposition, and we can invoke law of excluded middle to say that proposition is either true or not true. Okay, so by example 2, which is that for all epsilon in delta, it is not true that epsilon is not equal to 0. We can actually conclude for all epsilon in delta, epsilon is equal to 0. And this fact of saying, okay, if you have an OR and one of the statements of the OR leads to a contradiction, we can just conclude the other statement. That's constructively valid. It uses the principle of explosion, but it's fine. It all works. So we have that for all epsilon in delta, epsilon is equal to 0. So this implies delta is just equal to the set with only 0. Because every point in delta is 0. But by example 1, we get a contradiction. Because example 1 shows that delta is not just a set with only 0. Thus, because you got a contradiction, we're done. Yes.
How do you know what axioms you're allowed to use in this theorem? Because it's sort of independent of this one the axiom. So are you just allowed to use the other ones?
So when you're saying axioms,
Axioms of logic.
Yes. So we're allowed to use every axiom that we normally use in logic, except law of excluded middle.
Because we're proving
Well, so not just because of that, but because the logic of synthetic differential geometry is constructive logic. So in synthetic differential geometry, you assume all the axioms of constructive logic, and then you also assume the Cook-Lauber axiom and a few other axioms. So what I was proving here is that in constructive mathematics, you cannot also assume the law of excluded middle. You actually forbid it because it leads to a contradiction. So this is an example of how in synthetic differential geometry, you're forced to reason constructively. Because you can't reason classically anymore because it leads to a contradiction. Okay, so this was a lot. And you might have noticed, I kind of just moved the goalpost, right? I said, oh, constructive mathematics is useful because we can use it in synthetic differential geometry. I didn't actually say why this is useful. So let me go into why synthetic differential geometry, why synthetic differential geometry actually is useful. And this is because there's actually a subset of synthetic differential geometry called smooth infinitesimal analysis. And it's a way of doing, like an introductory calculus or introductory analysis using these ideas of epsilon. So to show this, I'm going to show the quotient rule. So first off, given two functions, f and g, from the smooth real line to the smooth real line, along with the proof. And so for all x in the smooth real line, g of x is not equal to 0. Then we can construct a function that we denote f divided by g, that's just equal to f of x over g of x. The reason this works is because we have a proof that g of x is not equal to 0. So it has a multiplicative inverse. So we can always divide by it here. Nice. Okay, so what is f over g prime? Okay, so to show this, we're going to use a similar idea that we used before when we were dealing with the identity function. We're going to find the derivative of f over g at x in two different ways. And then conclude by the Cook-Lauber axiom that the values we get have to be equal. So the first way, we have that f over g of epsilon. So for all epsilon, for all epsilon and delta, f over g of epsilon is equal to f over g of 0 plus f over g prime of 0 times epsilon. Right? And so this is actually just equal to f of 0 over g of 0 plus f over g prime of 0 epsilon. Okay, so this is the first way, right? And now we're going to construct, now we're going to find the value of this in the second way. So f of g, f divided by g of epsilon is also equal to f of epsilon over g of epsilon by the definition of f over g. And this is equal to f of 0 plus f prime of 0 epsilon divided by g of 0 plus g prime of 0 epsilon. Does this follow, everyone? So now here's the fun little trick, right? We have that for all x, g of x is not equal to 0, right? What we can conclude is that g prime of 0 epsilon is not equal to g of 0. So we can show g of 0 is not equal to g prime of 0 epsilon. And the reason for this is actually okay, it's a bit messy, but g of 0 is not equal to 0, right? G prime of 0 times epsilon is an infinitesimal, and this is because any number of the smooth real line times an infinitesimal is an infinitesimal because multiplication is commutative. So when you square this, you get g prime of 0 squared, epsilon squared equals 0. So we have g of 0 is not equal to 0. And since g prime of 0 times epsilon is in delta, we have by our earlier example too, that g prime of 0 epsilon is not equal, it is not true that g prime of 0 times epsilon is not equal to 0, right? But this means that these can't be equal, because if g of 0 was equal to g prime of 0 epsilon, then we have g of 0 is not equal to 0, but we also have that not g of 0 is not equal to 0. So we can conclude, thus, g of 0 is not equal to g prime of 0 times epsilon, all right? Which implies g of 0 minus g prime of 0 epsilon is not equal to 0. So this has a multiplicative inverse. We can divide by this. So if you go over here, if we multiply on the top and bottom by g of 0 minus g prime of 0 epsilon, we get that this top part, let me just erase this part so I have room for it. We get that this top part is equal to f of 0, g of 0, plus f prime of 0, g of 0, minus f of 0, g prime of 0, times epsilon. And this is because if we sort of multiply this out, we get this term, we get these two terms. But then we don't get this final term because the epsilon squared. And because we have epsilon squared, that's equal to 0, so that term cancels out. And then for the denominator, you can almost think of these as conjugates, right? Because we get g of 0 squared, and then the two intermediate terms cancel out, and then we get minus g prime of 0 squared epsilon squared, which is just 0. So this denominator is just g of 0 squared. And so from this, we can finally conclude, taking off the non-infinitesimal part, get f of 0 divided by g of 0. And then we also get f prime of 0, g of 0 minus f of 0, g prime of 0, divided by g of 0 squared times epsilon. And then, because we calculated the derivative in two different ways, we have this way, and then we have this way, we get that f over g the prime of 0 is equal to this term down here, which is exactly the quotient rule. And so I did make this a bit simpler because I've only looked at the case with just 0. This is actually not a problem. You can use so there's a quick little argument that you can make. I'll leave it as an exercise that you can conclude the exact same proof works for any x. You just have to look at x plus delta instead of just delta. But yeah, so we can conclude from this that the quotient, right? X. Okay. And so I do have a bit of extra time, so I'm actually going to go into one final step. And this is just going to make rigorous the notion I was talking about before about calculating the derivative in two different ways. All right. So this final bit is known as micro-cancellation. And this is just something that's used throughout. So micro-cancellation so what this says is that if for some points A and B on the smooth real line, we have that for all epsilon in delta, A times epsilon is equal to B times epsilon, then A is equal to B. So we can't divide by individual epsilon because they're not equal to 0. We don't have a multiplicative inverse for them. But we can do sort of this division where we show that for all infinitesimals, this equality is satisfied, then we can sort of divide, is the intuition behind it. So the proof of this is actually not too bad. It's basically the exact same idea we had before of calculating the derivative in two different ways. So we have, so consider, consider f of x is equal to a minus b of x, right? Okay, so we're going to calculate the derivative of f of x in two different ways. So f of epsilon, so for all epsilon in delta, f of epsilon is going to be equal to f of 0 plus f prime of 0 epsilon, right? But f of 0 is just going to be 0, and so this is just going to be f prime of 0 epsilon. However, we also have that we could just plug in epsilon into this equation. So this is also equal to a minus b of epsilon, right? So this follows, classical intuition. The derivative of a minus b times x is just a minus b. However, expanding this, we get a epsilon minus b epsilon. And then by our assumption that for all epsilon in delta, a of epsilon is equal to b of epsilon, a times epsilon is equal to b times epsilon, we can conclude that so because of this, and because for all epsilon in delta, a of epsilon is equal to b of epsilon, A of epsilon minus B of epsilon is equal to 0. So this is also just equal to 0 times epsilon again. And then by the uniqueness, you get that 0 and A minus B have to be the same. So thus, A minus B is equal to 0. And so A is equal to B. And so this exact idea is just the general principle for how we derive the derivative over here. Okay, so I went through that a bit quickly. Apologies about that. Does anyone have any final questions? All right, so to wrap up, first today I introduced constructor mathematics, right? I explained that it's classical mathematics, but you don't have access to the law of excluded middle. And then went over some of the ways it kind of breaks mathematics. And then I decided to go into a situation in which you're forced to use constructor mathematics. It's no longer just a choice that some people make, maybe because they want an extra challenge or anything like that. It's specifically because in this situation, we're dealing with anti-classical axioms. Classical logic does not work here anymore. We actually proved law of excluded middle is false. But I still showed how we can recover a lot of the same ideas. We still have proof of negation, for example. We still have, introductory calculus like proportional and things like that. And so this is an example of how you can actually apply constructor mathematics in ways that's not just, being like unnecessarily restrictive in what laws you can use. Right. Thank you.
All right, do we have any questions for Sean?
So, sorry, maybe a silly question, but it all feels a little bit contrived to me because couldn't you just like adjoin epsilon to some R and then call that the smooth real
Yeah,
line, and then draw these axioms, because then you don't necessarily show that the line is false because you have that it's either 0, it's either epsilon or a real number.
Yeah. So you could go about this a bit more like, I guess, like the contrived way, where you sort of have the smooth real line forms a field, except it's not just that it's not equal to 0; it has the lines like the original real numbers or stuff like that, and you can restrict what you're doing. I guess the one reason that people don't do this, I think, is that all this actually falls really naturally out of a specific field. So I'm not going to go too deep into this, but this stuff actually falls out of Topos theory.
Right.
Yeah. And so the reason for that is, the reason this comes about is because in Topos theory, constructor mathematics actually plays a really central role. In the same way how I was saying constructor mathematics has to be used here, if you're dealing with general toposes, you have to use constructor mathematics. And so one thing that's actually nice and a bit of a historical note I didn't really touch on is that we didn't just come up with these axioms. We looked at specific topi and then found that these are the axioms they satisfy. And so it's sort of like this is an afterthought of how we can actually just start with the axiomatic formulation first. And it's a bit easier to reason about it if you start it that way. You don't have to explain what topi are. So that's sort of why we're doing it this way instead of doing it maybe a bit more contrived way that still preserves law of excluded middle.
Can you tell us what's the difference between the synthetic mathematics and the constructive mathematics?
From what was the first word?
Synthetic.
Oh, synthetic. Yeah. So synthetic just in general refers to taking an existing subject in mathematics and generalizing it as far as possible, if that makes sense. So with Euclidean geometry, you could think about just points on like a plane and stuff and lines between them and all that, and that'd be your only model that you're dealing with. But using the abstractness of Euclidean geometry, we can apply it to other situations such as spherical geometry. That's actually how spherical geometry came about. People realized that if you drop the parallel postulate, you can now talk about different mathematical objects, but in the same way that you were talking about them before. Constructive mathematics in general is just mathematics without the law of excluded middle. You can do non-synthetic constructive mathematics. There are things where you take the real numbers and then see what sort of funky stuff happens there. It's just that in some situations, like synthetic differential geometry, you can't use the law of excluded middle. But in others, such as synthetic homotopy theory, you can. It just may break some things and may not break some things depending on what you do. And so, for example, in Euclidean geometry, it's synthetic, but you can't use the law of excluded middle.
make a very targeted
Yes.
comment? So you might be more familiar with Luchao, with the setting, like when you want to work with Infinity One categories, you can work with them as quasi categories or as logically enriched categories or as eagle categories or whatever. Working synthetically is not assuming you're in any specific model. So that's like the work that Emily's been doing. And that's what the word synthetic means, the exact same thing in this context. But it's not a synonym of constructive necessarily. It kind of resulted that it had to be constructive in this particular set of axioms. Sorry.
That's good.
Jenna?
Oh, yeah, so you were talking about why, like, the advantages of synthetic differential geometry, like, over the regular one?
Yeah.
Which you kind of did by giving us the quotient rule.
Yeah.
So, like, because I realized that, like, in physics, we a lot of times just look at, like, small things squared and we're just like, oh, it's gone. So,
Yeah.
like, I guess, is this just a better way to formalize it, or is there, like, more things that you can, like, do with it, rather than just, you know,
Yeah.
things that are not just, like, quotient rule?
No, yeah. So the code rule is just, again, a very easy example. I can go over without too much figuring it out.
Right.
So, in general, you can use this to formalize most of, I think, I'm not gonna say all because I don't know all of differential geometry, but you can formalize most of it.
Right.
But some of the usefulness comes out of, first, how like a sort of streamlined a lot of concepts can be. You can define jets and tangent bundles in really succinct ways. The second is that, naturality conditions in differential geometry falls out of this very nicely. I don't entirely know what that means, but I'm pretty sure I'm reciting that statement, right? Basically, there are some concepts that are important in differential geometry, but are normally hard to define. And in this setting, they kind of just fall out. They're very nice to work with. So there are more applications than just introductory calculus. And I think, I'm not actually sure of how much, like physics applications that people have actually used this for. I see that there's potential for it. I just don't know of any specific works. But yeah, so is that, okay. Yes.
We talked about a misconception of constructive mathematics and that a lot of people think that it's philosophy. I'm curious about the philosophical roots, like how did the initial like philosopher mathematicians develop the field?
Yeah. So initially, this came from the intuitionistic school of thought, which was all about denying the law of experimental in like philosophy, like in the real world. So it's like saying like, oh, can you really say tomorrow it will either rain or not rain if tomorrow like hasn't happened? And you can do philosophy in that way. There are like interesting things people have done and stuff on like a philosophical basis that, maybe it's not always right to say something's either true or false if we like don't know anything about it. So like, for example, some intuitionistic philosophers will deny that like, the Riemann hypothesis is true or false. We haven't shown that. We haven't shown anything like that. So they were denying something that existing. And so Brouwer, one of the main people who constructed mathematics in the early 20th century, was sort of along this school of thought. But then over time, people realized you can just kind of keep the fun math, and you don't necessarily have to take the extreme philosophical position of denying anything that uses law of experimental.
Gotcha, thank you.
Yeah.
I have a more philosophical question.
Yeah.
So I believe it was Saint Augustine who was said when he was trying to refute the skepticists that there are basically three kinds of definite knowledge. The one is inner knowledge, two is mathematics, the third is logic. But what you're saying here is seems to be that we can discard the axioms for logic quite arbitrarily. Does that mean we don't have definite knowledge in this area?
So I'm not a philosopher by most stretches, but I think one way to look at this is, I guess this is more of a structuralist point of view of mathematics than like a Platonist view. But you could play around with what axioms you assume. And then the question is, when you do that, do you gain access to things or do you lose access to things? Or is like there any uses you can use of that? So in this case, we can discard one of the axioms of logic to get like to reach new areas of mathematics. Right? But I'm not sure like philosophically, because like I'm not sure whether you can say like, oh, is this like not true because of that, or is normal logic not true because of that? I just think like the way I tend to think of this is that this is just kind of like a okay, as someone who's a structuralist, I tend to think of mathematics as like a game of rules that you assume and then you see the results of it. So I'm not really sure. Again, I'm not a philosopher, but how this sort of fits into a notion like that of when there's three truths like such as mathematics and then also logic.
You said you're a structuralist. What
Yes.
other isms are there?
I think the main one is Platonist. So the idea with Platonist is that mathematical objects are, okay, I may be butchering this, I'm not a Platonist, but the idea is that mathematical entities are like out there and you discover. And this is actually a view I had for a while. And then when I started going more into constructive mathematics, it's more like, okay, we're just assuming rules, and then we can see what those implications of those rules are. But like, I don't think, the smooth real line is like any more or less of a real thing than the normal real numbers. Yeah, there's, again, philosophy math is a very big subject, and it's actually surprisingly not that connected to regular mathematics. There's a lot of like a lot of mathematicians don't think too much about philosophy mathematics, which isn't like a good or bad thing, it's just the thing. So yeah, so there's definitely a lot more people could say about that stuff.
I have a question back
Yes.
to the Roland. Now, do you know if you can get like manifolds and stuff in synthetic differential calculus?
Yeah. So I didn't really talk about the smooth real line, but you can talk about abstract spaces like, I'm not actually sure exactly what axioms you use in this, but you can define things like functions from delta to like an abstract like manifold and stuff. And the cool thing about this is that when you start talking about stuff like that, you're not specifically talking about smooth manifolds. You're just talking about things that satisfy these sort of axioms.
Right.
And so you can prove things about smooth manifolds and smooth maps, which are like the basis of the synthetic stuff. But you're also proving things about way more complicated stuff. And it's really cool because at the same time as proving stuff about smooth manifolds, you end up also proving some really nice things about algebraic geometry structures, because a lot of the topoi you use come from algebraic geometry. And I think it's actually an active research question. What applications does synthetic differential geometry have to algebraic geometry structures? So you can prove stuff about smooth maps, but I don't think you can just prove stuff about only smooth maps. You end up proving things that also satisfy the axioms.
Do you have any further questions?
Can you comment on the original question?
Yes, the homotopy type theory. So homotopy type theory is normally done constructively. It doesn't have to be. That's actually, it's completely consistent with that univalence and all that other stuff, and then also log excluded. It's just that if you do things constructively, you get some really nice structures out of it. One thing is that because equality is not decidable, you can get some structures that, let's see, how does this? You can encode some topological information. I'm using topological encodes because it's more complicated than just being topology. But you can encode some topological notions that are much more nuanced than you would from like classical mathematics. Yeah.
I thought you said that every result that holds without the LEM has to also hold within normal mathematics.
Yeah. It's
So
just
if you get a result instead of this constructive mathematics, you could necessarily apply that.
yeah. It's just that in some places you can prove things inside constructive mathematics that you can easily prove outside constructive mathematics and classical mathematics. But if you want to apply to something that maybe is anti-classical, then you need to sort of pull it back and prove it just in constructive mathematics.
So maybe think about synthetic homotopy or synthetic
Yeah. So
topology.
yeah. So it ends up being that if you use a specific kind of type theory and stuff, you can start to axionize synthetic homotopy theory, and that's usually done constructively. And so yeah, I can go to some examples probably like once if you want to stay back and whatnot. But in general, constructive mathematics is usually used in homotopy type theory, but it doesn't have to be. And there are some good reasons to not use it. For example, I think Martin Escardo proved that the Cantor-Bernstein theorem. So the whole thing from like if you have injection and surjection, you can get bijection. They proved that is actually equivalent to the long excluded method. In homotopy type theory, I think, or something like that. Maybe you need choice of another. Something like that. Yeah. So you can still assume things, and people who do constructive mathematics do assume the long excluded middle sometimes if they need it. But in general, they try to prove things without it.
I'm sorry, Cantor-Bernstein doesn't hold instead of synthetic homotopy,
It's equivalent to long excluded middle.
which doesn't hold instead of synthetic.
No. In synthetic homotopy theory, it's just not safe. Synthetic
So
homotopy
so
theory.
it's not like a knot.
Yeah,
It's
exactly.
just like a
Misconception
whatever.
number 2. Yeah. So in synthetic homotopy theory, you just don't comment on whether it's LEM or not. But in synthetic differential geometry, you do comment. You say no, it's false. Yeah. So that's actually like an important thing. Is that again there are uses of constructive mathematics in places where you could assume long excluded middle, but there are like reasons not to. It holds for like slightly different purposes if you don't. You can apply to slightly more minutes. Yeah.
Is this related to Lovery's other works? For example, his work on differential cohesion and also trying to make certain philosophical concepts concise like Hegel and Marx?
So I actually do not know much about that area. Like I know one of Lauber's goals was formalizing physics in a certain way. I'm not actually sure how that's related to other Lauber's ideas, but I would not be surprised if it did in some way. Yeah. All right.
Do we have any further questions?
All right. Please.
All right, let's first thank our speaker once again.